Good day, everyone. This video is created using AI voice, but the text was created and approved by Sinika Albaye, the OpenDSU project leader. Today, I have the privilege of introducing a seminal project in the domain of decentralized data sharing, OpenDSU, under the leadership of Axiologic Research from Iași, Romania. This project, a beacon of innovation in the open source community, has garnered significant attention and support not only from Romanian research groups, but also from broader European research initiatives, notably the Horizon 2020 PharmaLedger project. OpenDSU stands at the forefront of revolutionizing how data is shared and managed in a decentralized environment. It embodies a groundbreaking approach to data sharing, one that is secure, efficient, and user-centric. This framework is not just a technological advancement. It is a paradigm shift in the way we think about data sovereignty and privacy in the digital age. At the heart of OpenDSU's data sharing capabilities is its robust and flexible architecture, designed to cater to a wide range of use cases and industries. From healthcare to finance, OpenDSU offers an unprecedented level of control and security, allowing organizations to share sensitive data with confidence and integrity. Today's presentation will delve into the intricacies of OpenDSU's data sharing features, exploring how it leverages cutting-edge technologies to ensure data privacy and security while maintaining ease of use and interoperability. We will also examine real-world applications and the impact of OpenDSU on various sectors, highlighting its potential to transform industries and empower organizations and individuals alike. Stay with me as we embark on this exciting journey to explore the vast capabilities and promising future of OpenDSU in the world of decentralized data sharing. Let's start with some generic theory before explaining the OpenDSU specific approach to data sharing. In discussing data sharing between independent organizations, three distinct patterns emerge, each with its unique approach and implications. The first pattern, push of heavy messages, involves sending messages containing complete datasets to partners, akin to file transfers. This method is straightforward but can be inefficient and lacks the nuanced data integrity offered by more advanced blockchain technologies. The second pattern, pull light messaging, represents a more refined approach. It involves sending access keys to partners, allowing them to pull data as required while maintaining the source of truth with the data's creator. OpenDSU data sharing aligns with this pattern, emphasizing the importance of data integrity and controlled access. This method offers a balance between data accessibility and security, ensuring that data is available when needed but remains under the control of its originator. The third pattern centers on the use of shared or distributed databases, such as blockchain and distributed ledger technologies. These systems are based on shared data structures within databases. This pattern is particularly effective for public data or scenarios where data integrity and immutability are paramount. However, it's not without challenges. The use of complex and as yet unproven technologies like zero-knowledge proofs, ZKPs, can introduce complications. Furthermore, this pattern can suffer from scalability and performance issues, making it less suitable for certain applications. While the push of heavy messages pattern offers simplicity, it lacks the advanced data integrity features of blockchain technologies. The pull light messaging pattern, exemplified by OpenDSU, strikes a balance between accessibility and control, maintaining data integrity. Lastly, the shared or distributed database pattern, although robust for certain applications, faces challenges in scalability and the maturity of its underlying technologies. Each pattern has its place, but the choice depends on the specific requirements of data sharing and the desired balance between accessibility, control, and integrity. In this slide, we present the high-level approach of OpenDSU-based communication, crucial for sharing data pertaining to the states of business processes between two partners, though it can be generalized to any number of partners. The image exemplifies a generic architecture on how two entities, each with their own operational systems, leverage OpenDSU to efficiently manage and exchange data relevant to their business processes. Initially, Partner 1 and Partner 2, utilizing systems such as SAP, begin their collaborative process, or we could say choreography. Their respective DSU Smart Wallets applications act as vital intermediaries in this process, skillfully handling and preparing the data for transfer. This data is then processed, being transformed into a variety of formats including EPCIS and wrapped in universally accepted formats like XML, PDF, and JSON. This conversion is critical to ensure seamless compatibility and uphold the integrity of data across different systems. At the heart of this exchange is the use of decentralized identifiers, DIDs, establishing a secure and verifiable link between the partners. This secure connection not only fosters reliability, but also maintains the confidentiality and integrity of the shared data. The procedure further encompasses the exchange of keys and the transfer of data sharing units, DSUs, between the partners, an essential step for maintaining robust access control and data security. To guarantee the safe transit of this data, DID-based message queues are utilized, ensuring data protection throughout its journey. Upon reaching its destination, the data can be used or stored in databases, while the original data from the DSU, the off-chain data, remains with the original creator. This arrangement is connected to a blockchain network, which provides an immutable and traceable record of all transactions and interactions involved in the data sharing. The blockchain network, complemented by its nodes, strengthens the system, offering a decentralized and secure environment. This framework not only bolsters the security of the data exchange, but also enhances the trust and reliability of the entire process. We hope that now we have a clear overview of how OpenDSU enables effective data sharing and management of business process states between partners, underscoring the efficiency, security, and dependability of this advanced method of communication. In the following slides, we will go into some details on how the light messaging pull approach for data sharing works in OpenDSU-based systems. In this diagram, we highlight the first phase of data sharing with OpenDSU, which we call DSU-fication of data, or sometimes bricking or brickification of business data. This means storing the data in encrypted bricks in the off-chain storage and anchoring those bricks in the blockchain. In the blockchain, we store anchors that have hash links to the bricks. For more details, check the OpenDSU technical presentations. The control of the DSUs is managed by the encryption keys that can be used to decrypt the encrypted bricks and by the signing keys for the anchors. OpenDSU automates both the encryption and the authentication of the data using digital signatures through a concept called keys. The keys come in families that start with a powerful key capable of read and write operations, which can be derived into keys with lesser power, for example, only for reading or only to prove that some data is anchored and is identifiable in a blockchain or a distributed ledger. The powerful key used to initiate the DSU is stored in the digital wallet of the entity that owns the initial version of the DSU. The second phase of data sharing is simply authentic communication with a partner using the partner's DID. The key that allows writing in the DSU, or a derived key that only permits reading from the DSU or a part of it, is simply added to the message queue of the partner with whom the sharing is desired. The communication is authenticated using public-private key cryptography. The message is signed and encrypted by the initiating partner's DID and can only be decrypted with the private key of the partner who controls the destination DID and identifies the message queue. A Diffie-Hellman key exchange is used by default in OpenDSU implementations. The concept of DSU can exist outside of the W3C DID's implementation offered by OpenDSU, but some concepts like BDNS allow the implementation of IDD methods that are easy to understand and use by programmers and architects. In the third phase of DSU sharing, a partner's system with access to the wallet will retrieve this shared key SSI and can simply reconstruct the DSU using remotely stored data. The receiving partner in the data sharing process will be able to directly use the DSU data or import it into databases. The DSU concept is constructed to allow sharing to be asynchronous, as can be observed because distributed systems generally work in an asynchronous way. The blockchain is used to ensure that the data transferred is authenticated and its integrity verified, while the actual storage of the data can remain with the partner that creates it. Even in scenarios where multiple partners are updating a common DSU, the bricks could stay on separate BDNS domains, indicating that the data remains with its creators. OpenDSU is flexible. It is possible to share off-chain data by default, by using something like IPFS or a distributed database or file system for storing bricks. However, in scenarios involving independent companies working together, it is not advisable from a security and data trust point of view to use a shared database except for a full-fledged blockchain or distributed ledger. The DSU anchoring, sharing, and usage slides together paint a comprehensive picture of the secure data sharing approach proposed by OpenDSU. The DSU anchoring element sets the stage, showcasing the initial steps in securing and storing data. Here, data is encrypted, transformed into bricks, and stored in near-chain storage, known as brick storage. A cryptographic imprint of these bricks is then anchored in the blockchain, ensuring data integrity and security. Next, the DSU sharing element builds upon this foundation, focusing on the distribution of data. Key SSIs, which come in various forms to allow different levels of data access, play a crucial role in this process. These keys are shared with partners and stored in wallets, enabling controlled access to the DSU. The sharing occurs through mechanisms like message queues, MQs, secured further by decentralized identifiers, DIDs, and verifiable credentials. Finally, the DSU usage element exemplifies how data is accessed and utilized. Entities with the right key SI can pull the encrypted data bricks from partners and reconstruct the complete dataset. This reconstructed data can be used directly or imported into databases for various purposes, offering flexibility in data handling. Together, these slides present the basic concepts of DSU technology, showing how each component works in unison to provide a secure, efficient, and flexible data management system. They highlight the seamless integration of encryption, blockchain technology, and controlled access, ensuring data integrity and security while catering to a wide range of data sharing and usage needs. Now that we've explained how DSU sharing works, it's important to note that for a successful system, DSUs need to be designed as granularly as possible, especially in terms of access control. Essentially, the issue resembles the normalization of data in a relational database, but now breaking a data model into entities requires analysis of the data sharing method. The basic rule is that if a set of fields or metadata will be shared together, then they should naturally be put in the same unit or the same DSU. Of course, it's also important whether the sharing is done in read-only or write mode. Generally, an insight from multiple enterprise use cases is that read-only sharing is sufficient in 99% of cases. The only more common scenario where write mode sharing of DSUs is absolutely necessary is to maintain the state of a business process. This state can be imagined as an automaton in which the current state of the process is kept shared and can be updated by different entities. If you have such cases, or if you want to implement a kind of smart contract shared between multiple entities in the network, but still want to use DSU's ability to keep data private, we recommend analyzing the OpenDSU concept of SVD, self-validating data, and maintaining such an SVD within the shared DSUs. In this way, it can be elegantly verified whether the process's evolution complied with the planned rules, while also allowing the right sharing of the smart contract off-chain. As we approach the end of the first phase of the presentation, I want to summarize the advantages of OpenDSU in secure data sharing between independent companies. Firstly, we must acknowledge the insight that proposing the key SIs and DSU concept for data sharing is likely a very powerful tool not found in other enterprise blockchain technologies. These concepts seem to us as fundamental as the idea of a file or the RPC concept. Advantages of sharing data through the communication of access keys, key SIs, manifest in several key areas. First, the process is secure and auditable, with blockchain technology ensuring the integrity of the original data during sharing. This approach also empowers decentralized access control and self-sovereignty, making key SSIs particularly effective for robust data sharing across different entities. Additionally, granular access control is a significant feature, enabling specific permissions like read-only or write modes, thus offering finely tuned data access. In terms of scalability, this method is highly adaptable for handling large datasets and accommodating multiple users. Unlike file transfer methods or naive messaging, it utilizes pull mechanisms, meaning data is accessed as needed rather than being pushed at the point of sharing. This approach also aligns well with regulatory compliance, particularly in terms of data protection laws, as it supports proper data segregation. From a financial perspective, sharing data through KSIs is cost-effective. It eliminates the need for data duplication, thereby reducing storage costs. Finally, the dynamic management aspect is noteworthy. It allows for flexible data removal, such as deleting off-chain bricks and the rotation of cryptographic keys, all while retaining the anchor IDs. This ensures that data management remains fluid and adaptable to changing needs or conditions. In the second part, we aim to introduce the OpenDSU proposed architecture and specific components essential for the data sharing approach OpenDSU proposes. The diagram presents a generic architecture for an OpenDSU application, illustrating the intricate interplay of various components integral to its functionality, each labeled from 1 to 8 for clarity. Component 1, labeled System of Records, represents the core application servers, including complex enterprise resource planning systems like SAP. These serve as the primary repositories of organizational data and are crucial for maintaining business operations and records. In some cases, the DSU components are the master data, but in others, the source of enterprise data remains in legacy systems. Moving to Component 2, we have the off-chain database. This component plays a pivotal role in storing data not recorded on the blockchain, offering a complementary data management solution that works in tandem with the blockchain infrastructure. Component 3, DSU tokenization, involves importing data into data sharing units, DSUs. This step is critical for converting organizational data into a format suitable for blockchain integration, ensuring seamless and secure data tokenization. This component can take different forms, from APIs to enterprise wallets. Next, Component 4, Bricks, Storage, or Near Chain, refers to the OpenDSU storage solution located close to the blockchain, giving blockchain-like properties to the anchored data. It is designed for efficient storage and retrieval of data, bridging the gap between on-chain and off-chain data environments. Component 5, Cloud Enclaves for Enterprise Key Management, highlights the system's security aspect. It involves managing cryptographic keys in a secure cloud environment, ensuring that data access and transactions are protected and controlled. For Component 6, we have User or Enterprise Wallets. This component utilizes cloud enclaves for managing digital wallets, essential for transactions and interactions within the blockchain network. This could also take the form of APIs or OpenDSU digital wallets. Component 7 is the Business Intelligence component, an optional yet valuable component that could provide analytical capabilities. It enables the extraction of insights and intelligence from blockchain data, enhancing decision-making processes. Finally, Component 8 emphasizes the MQs for communication between partners. This component is essential for facilitating secure and efficient communication between different network participants. It recommends the use of decentralized identifiers, DIDs, and is secured with verifiable credentials, ensuring a high level of security and trust in communications. Together, these components illustrate the complex and multifaceted nature of a blockchain application network, each playing a specific role in ensuring the system's overall functionality and efficiency. The diagram is a zoomed-in view of the previously described enterprise blockchain network, offering a detailed look at the organizational level, encompassing the same 8 major components. Each organization within this network maintains its own system of records, such as application servers or ERPs like SAP, tailored to their specific operational needs. The diagram shows the implementation of user or enterprise wallets within each organization, leveraging the security of cloud enclaves for managing transactions and interactions on the blockchain. The slide further emphasizes the role of message queues in facilitating secure communication between partners, essential for collaboration and data exchange across the network. There is an MQ owned by each company, but the system interacts with MQs from other partners. Central to the diagram is the inclusion of a blockchain node controlled by each organization. This node is pivotal for maintaining the integrity and security of the network, ensuring that each entity has a direct and secure connection to the blockchain, thus enhancing the overall security and efficiency of the system. The final diagram presents an example that illustrates the life cycle of a data sharing unit, DSU, from a sharing perspective, effectively detailing the stages and decisions involved in the process. Initially, a new DSU is created, marking the beginning of its life cycle. This DSU, as an encapsulated unit of data, is ready to be integrated into various business processes. The first significant decision in this cycle occurs when a business process chooses to share this DSU in a read-only mode with a partner. This decision reflects a controlled sharing strategy, where the partner can view or analyze the data without the ability to alter it. As the DSU continues through its life cycle, another phase of the business process might opt to share the same DSU in a write mode with a different partner. This stage represents an increase in the level of trust and collaboration, granting this partner the capability to access and modify the data within the DSU. Throughout these sharing phases, all communication is rigorously secured. Message queues, MQs, play a vital role in this security architecture by transmitting encrypted messages. The encryption is facilitated through a key exchange mechanism between the decentralized identifiers, DIDs, of the involved partners, ensuring that only authorized entities can access and interpret the messages. Optionally, the system can further enhance security and trust by incorporating verifiable credentials. These credentials provide additional layers of authentication and authorization, ensuring that each transaction or data exchange complies with the defined protocols and standards. Thus, this diagram clearly outlines the progression of a DSU from its creation to various levels of data sharing, underpinned by robust security measures. It reflects the dynamic and secure nature of data management in contemporary digital ecosystems. Thank you for viewing this presentation. We invite you to explore the OpenDSU channel for additional presentations. There, you can find a range of topics, including the generic OpenDSU presentation on building digital trust ecosystems, tailored for a business-oriented audience, a comprehensive keys management presentation, and an overview of OpenDSU concepts designed specifically for those with a technical background.